Microsoft has entered into a groundbreaking agreement to purchase nuclear fusion energy, becoming the first company to do so. They are placing their confidence in the potential of next-generation fusion technology to generate electricity on a commercial scale by 2028. The deal was made with Helion Energy, a fusion research firm that aims to construct a 50 megawatts fusion power plant within the next 5 years. Despite the significant research challenges that still need to be overcome, Helion is optimistic about their ability to deliver the world's first fusion power facility. Nuclear fusion is a promising technology that seeks to replicate the natural reactions occurring within the Sun, offering a nearly limitless source of energy. It is often referred to as the holy grail of clean energy because it doesn't rely on fossil fuels and produces no hazardous waste. In recent years, scientists have made notable breakthroughs in fusion research. The Lawrence Livermore National Laboratory achieved the first-ever fusion ignition, marking a significant scientific achievement. However, commercial-scale fusion is expected to take at least a decade due to the complexity and cost of scaling up the process. Microsoft's decision to bet on achieving commercial fusion within half that time aligns with their commitment to becoming carbon negative by 2030. Their goal is to remove more carbon from the environment than they emit, with a long-term ambition to eliminate all their historical carbon emissions since their founding in 1975. Microsoft's president, Brad Smith, expressed optimism about fusion energy's potential to support the world's transition to clean energy. The collaboration with Helion Energy aligns with Microsoft's clean energy objectives and aims to accelerate the adoption of a new, efficient method of bringing clean energy to the grid. Fusion energy is a potential source of energy that aims to replicate the process that powers the Sun and stars. It involves the fusion, or joining together, of atomic nuclei to release an enormous amount of energy. In the core of stars, including our Sun, the intense heat and pressure cause hydrogen nuclei to collide and fuse, forming helium. This fusion process releases an enormous amount of energy in the form of light and heat. Scientists are attempting to recreate this process on Earth to harness fusion energy for practical use. The most commonly researched fusion reaction for energy generation involves the isotopes of hydrogen, deuterium and tritium. These isotopes are heated to extremely high temperatures, typically in the range of hundreds of millions of degrees Celsius, creating a plasma state where atoms are stripped of their electrons. At such high temperatures, the atomic nuclei have enough energy to overcome their mutual electrostatic repulsion and can come close enough for the strong nuclear force to bind them together, releasing energy. One of the main challenges in achieving practical fusion energy is confining and controlling the superheated plasma. Different approaches have been pursued, including magnetic confinement and inertial confinement. Magnetic confinement relies on powerful magnetic fields to trap and control the plasma, preventing it from touching the walls of the containment vessel. The most well-known magnetic confinement device is the tokamak, which uses a toroidal chamber to confine the plasma. Inertial confinement, on the other hand, involves compressing and heating a small pellet of fusion fuel, typically with high-energy lasers or particle beams. The extreme conditions created by this compression cause the fuel to reach fusion conditions for a brief period. Fusion energy has the potential to provide numerous benefits. It offers a virtually limitless supply of fuel, as the primary fuel sources, deuterium and lithium, are abundant in seawater. Fusion reactors would produce minimal waste compared to traditional nuclear fission reactors, and there would be no long-term storage of radioactive materials. Additionally, fusion reactions do not produce greenhouse gases or contribute to climate change. While significant progress has been made in fusion research, building a practical and economically viable fusion power plant remains a complex engineering challenge. However, scientists and engineers worldwide are dedicated to advancing fusion research and developing viable fusion energy technologies. The history of developments in fusion energy spans several decades and includes significant milestones and breakthroughs. The foundational principles of fusion were established during 1920s to 1940s. Physicists such as Arthur Eddington and Hans Bethe laid the groundwork for understanding the processes occurring in stars and the potential for harnessing fusion as an energy source. Post-war, in the 1950s, researchers began actively exploring fusion as a source of energy. The establishment of research facilities like the United Kingdom Atomic Energy Authority, UKEA, and the Soviet Union's tokamak experiments marked significant milestones. During this time, the tokamak emerged as a leading device for magnetic confinement fusion. In 1968, the first significant fusion reaction occurred at the Soviet Union's Joint Institute for Nuclear Research, JINR, with the tokamak device. In 1973, the JET, Joint European Torus, experiment in the United Kingdom achieved the first controlled release of fusion energy, demonstrating the potential of fusion as a viable energy source. The 1980s witnessed significant advancements in tokamak technology. The Soviet Union's tokamak device, T-15, set a record for plasma confinement time. The Joint European Torus, JET, achieved significant fusion power milestones. In the 1990s, the International Thermonuclear Experimental Reactor, ITER, project was initiated as a global collaboration to develop a practical fusion power plant. 1970s to 2000s, inertial confinement fusion, an alternative approach to magnetic confinement, also made progress. In the 1970s, the first experiments using laser-driven implosions took place. In the 1990s, the National Ignition Facility, NIF, in the United States was established, aiming to achieve self-sustaining fusion reactions through laser-driven compression. In the 2000s, various experiments achieved important milestones. The Large Helical Device, LHD, in Japan set records for plasma confinement. The National Ignition Facility, NIF, in the United States aimed to achieve ignition and energy gain. The ITER project, with involvement from multiple countries, entered its construction phase, representing a significant step toward realizing a practical fusion power plant. In recent years, there have been notable advancements. In 2020, the Wendelstein 7X stellarator in Germany achieved a plasma confinement record. The National Ignition Facility, NIF, achieved a major milestone in fusion yield, though not yet reaching ignition. Private companies like Helion Energy and Commonwealth Fusion Systems have emerged, pursuing innovative fusion approaches and attracting significant investments. While substantial progress has been made, the journey towards practical fusion energy continues. Scientists and engineers worldwide are dedicated to addressing the technical challenges and refining fusion technologies to achieve sustained energy gain and develop economically viable fusion power plants. Fusion energy is often considered superior to fission energy for several reasons. Fuel availability. Fusion energy utilizes isotopes of hydrogen, deuterium and tritium, as fuel sources, which are abundant in seawater and easily accessible. In contrast, fission energy relies on uranium and plutonium, which are finite resources and require mining and enrichment processes. Fuel efficiency. Fusion reactions release a significantly larger amount of energy compared to fission reactions. A single gram of fusion fuel can produce many times more energy than a gram of fission fuel, making fusion highly efficient in terms of fuel utilization. Safety. Fusion reactions are inherently safer than fission reactions. Fusion reactors do not operate with a chain reaction or risk meltdowns like nuclear fission reactors. In the event of any issue or disruption, fusion reactions cease, reducing the risk of accidents or catastrophic releases of radioactive materials. Waste generation. Fusion reactions do not produce long-lived radioactive waste as fission reactions do. While fusion reactors produce some low-level radioactive waste, it decays relatively quickly, making it easier to handle and dispose of compared to the long-term storage requirements of fission byproducts. Radioactive risk. Fusion reactors do not involve the use of fissile materials like uranium or plutonium, which are highly radioactive and pose security risks in terms of theft or proliferation. Fusion fuel is not suitable for nuclear weapons, reducing the risk of nuclear weapons proliferation associated with fission technology. Environmental impact. Fusion energy has minimal impact on the environment. It does not produce greenhouse gas emissions or contribute to air pollution. Fusion reactions only require small amounts of fuel, resulting in lower mining activities and environmental disruptions compared to fission. Stability and control. Fusion reactions require precise and controlled conditions to occur, making it easier to control and shut down the reaction if needed. This stability and control enhance the safety and reliability of fusion reactors. It's worth noting that while fusion energy offers these advantages, it is still a developing technology and faces significant engineering challenges. Building practical fusion reactors that can consistently achieve net energy gain and operate economically remains a complex task. However, ongoing research and advancements are aimed at overcoming these challenges and realizing the full potential of fusion energy. Fusion energy holds several significant implications for various aspects of society, energy systems, and the environment. Here are some key implications. Abundant and clean energy. Fusion energy has the potential to provide a nearly limitless supply of clean energy. It relies on abundant fuel sources like deuterium and lithium, which can be extracted from seawater. Unlike fossil fuels, fusion does not produce greenhouse gas emissions that contribute to climate change. It offers a sustainable and environmentally friendly energy solution. Energy security and independence. Fusion energy can contribute to energy security by reducing dependence on traditional energy sources. With fusion, countries could potentially generate their own energy domestically, reducing reliance on foreign energy imports and geopolitical vulnerabilities associated with traditional energy supply chains. Mitigating climate change. Fusion energy can play a crucial role in mitigating climate change. By offering a carbon-neutral and clean energy alternative, it can help reduce greenhouse gas emissions associated with electricity generation. It could potentially replace fossil fuel-based power plants, leading to a significant reduction in global carbon emissions. Economic opportunities. The development and commercialization of fusion energy can create significant economic opportunities. It can spur innovation, research, and development in various sectors, including engineering, materials science, and advanced manufacturing. Fusion energy could lead to the growth of new industries, job creation, and economic growth. Energy accessibility. Fusion energy has the potential to provide energy access to regions where traditional energy infrastructure is lacking or underdeveloped. Its scalability and ability to generate large amounts of power could help meet the energy needs of remote areas and developing countries, fostering economic development and improving quality of life. Waste reduction. Fusion reactions do not produce long-lived radioactive waste like traditional nuclear fission reactions. While there are still challenges associated with fusion reactor materials, fusion has the potential to significantly reduce long-term waste management concerns compared to conventional nuclear power plants. Scientific and technological advancements. The pursuit of fusion energy requires scientific breakthroughs and technological advancements. As researchers work on developing fusion technologies, it drives progress in fields such as plasma physics, materials science, superconducting magnets, and advanced engineering techniques. These advancements can have broader applications and spin-off benefits beyond fusion energy itself. It's important to note that while fusion energy offers great promise, there are still significant technical and engineering challenges to overcome before it becomes a practical and commercially viable energy source. However, ongoing research and investments in fusion are aimed at addressing these challenges and realizing the potential benefits fusion energy can offer.